Okay, hello everyone, and welcome to the 15th in our Fault2SHA learning series. Welcome back after our summer break. As always, the purpose of this learning series is to really help all of us who are working in using faults in seismic hazard analysis to try and work with people across different disciplines with different expertise, and to help us understand all those detailed seminars and research presentations we go to, and all the papers from hearing from the very experts in all the different disciplines. Today, I'm absolutely delighted to have Chris Goldfinger with us today, the Professor Emeritus from the College of Earth, Ocean and Atmospheric Sciences at Oregon State University. Chris is, I'm sure, known to many of you. He has been cited by many of us. He has over 5,000 citations, according to Google, with papers looking at paleoseismology, particularly turbidite paleoseismology, sedimentology, and focusing on earthquake hazard and the Cascadia subduction zone. He's also seen regularly on many public-facing entities, including programs and radio, to name a few. He's given a TEDx talk. He's been on CNN, BBC, the History Channel, National Geographic, Discovery Channel. I could go on and on. I will pause there. He's also the advisor to the Oregon Safety Policy Advisory Commission, with many leading roles as well related to earthquake safety. So I'm going to pause there, because otherwise I could go on and on and on about all of Chris's achievements, but we just want to hear from him today. He's going to be talking about bringing together onshore and offshore paleoseismology, the next great Cascadia earthquake. How did we get there? He'll go through his presentation, and then there will hopefully be a little bit of time at the end if anyone has any questions. So if you do have questions at the end, raise your hand or put them in the chat, and I can convey them through to Chris. So without further ado, I hand over to Chris. Thank you again. We really appreciate you being with us today.
Oh, thanks so much for the invitation, and thanks for your kind introduction as well. Let me share my screen. Well, thanks again, Joanna, for having me, and I'm happy to give a little talk about my favorite topic. I became a paleoseismologist a little bit by accident, and that'll be sort of woven into this, and so I'll tell the story at a I think pretty accessible level, and hopefully we'll have some time for discussion and questions. Okay, so probably everybody has seen this episode of The Big Bang Theory, where Sheldon rags on geologists for being not a real science. And the funny thing is, as a geologist, he's partly right. Geology is about 100 to 150 years behind most of the other sciences, and not really sure of the reason for that, but in any case, he's not completely wrong. And just as just to show to make the point, you know, in 1969, not that long ago, we were doing arguably the most advanced thing that humans had ever done. We're hippity hopping around the moon and so forth. This setting out a seismometer on the moon. And at that time, plate tectonics, the theory of everything in earth science, was really about 6 years old. It was really fully accepted just after the 1964 Alaska magnitude 9.2 earthquake. And so we're really just hanging on to the bottom rung of the ladder of understanding of earth sciences. It's that young, and we just had really no clue what was going on prior to the 1960s, except for Alfred Wegener, of course, who figured it out much earlier. And so here's Buzz Aldrin setting up a seismometer, and that seismogram at the bottom is the ascent stage of Apollo 12 hitting the moon just later that year. So with that in mind, Cascadia, which is here, the west coast of North America, this is what it would look like with the water drained out. Here's all the marine data showing channel systems and the submarine topography offshore. Cascadia played a role in the early days of plate tectonics in that the magnetic properties of the Juan de Fuca plate, which is this thing here, and the Gorda plate, were used to establish this new concept called seafloor spreading, where new seafloor was created at the mid-ocean ridges, like the Gorda Ridge and the Juan de Fuca Ridge here. And so there's a famous paper in 1963 by Vine and Matthews showing that, the age of the seafloor crust increased away from these ridges, and therefore new crust was being formed, and it was being destroyed at this thing called a subduction zone, which is the boundary here between the dark and the light. And so Cascadia played a role, along with other places around the world, mostly the Atlantic, in demonstrating seafloor spreading. And then once plate tectonics, zooming ahead, was accepted, it explained a lot of things. Linear rows of volcanoes were, parallel to subduction zones, the dipping series of dipping planes of earthquakes underneath continental margins, the Wadati, Benioff zones, and so forth. But Cascadia was forgotten, and it was forgotten because it was, for one main reason, it was seismically quiet. It didn't have a Wadati Benioff zone at all. It was completely silent. And so it was one subduction zone that just didn't fit in the new model of plate tectonics, that almost everything else seemed to fit well. And so sometimes when we have an outlier like that, we might just sort of tippy-toe around it and say, well, we'll get back to that. But it took 20 years or more, really, to get back to it and wonder about Cascadia. Why was it so quiet? Was it some sort of a standout anomaly, or was it, or what was it? It was just an unknown. And so about 1984 and 1985, a Canadian geologist named John Adams was the first to suggest that there actually was direct evidence of great earthquakes, magnitude 8 and up, in Cascadia, and it just hadn't happened in historic times. And he reasoned this out from deep sea deposits called turbidites, which are sometimes triggered by earthquakes, sometimes other things. And these turbidites were found offshore, and he, by sedimentologists who'd worked diligently to work out all the details of these things in the 1960s at Oregon State University. But and just at about the same time, a little bit later, Brian Atwater discovered this sequence in Willapa Bay, which is kind of innocuous looking, but what we have here is a marsh deposit on top, and then some subtidal bay mud here, and then a sheet of sand, and then an old marsh deposit, which has become peat. Now it's closed, and then more sand below that. And the thing about this, though, is that this marsh and the old marsh down here, which turned out to be about 300 years old, are the same plants. And their salt tolerance is much less than the distance you're seeing, which is about a meter between the modern marsh and the old marsh. So these plants could not survive at the same tide level that this evidence exists at. So Brian reasoned that either sea level had rapidly changed, or the land level had rapidly changed relative to the sea. And the latter was sort of an outrageous hypothesis. And so he reasoned that this old marsh used to be up at this level, but it was suddenly brought down to this level by a great earthquake. And then the sand sheet, he reasoned, was a tsunami sand sheet. And then the bay mud was this entire bay, Willapa Bay in Washington, which is right about here, had subsided about a meter, and so it stayed, and then it stayed down. So it became part of the bay, and only gradually was uplifted back to present day, where the new marsh surface is and where these plants recolonized it. And at the time, everybody thought this was completely outrageous because this type of land-based paleoseismology didn't exist. Brian was the first to do it, just as John Adams was one of the, not exactly the first, but the second or third person to use submarine deposits as indicators of past earthquakes. And so after lying fallow for 20 years, Cascadia started to become sort of a petri dish for this type of work. And then there was a pretty short distance between those two pieces of work and when this story was accepted. Basically, this to shorten this part of the story a bit, this peat deposit and some killed trees, their age was narrowed down to the winter of 1699. It had to have happened before that or after that time, and before the spring of 1700. And this is using tree ring dendrochronology. And what really sewed it all together was something called the Orphan Tsunami, a tsunami deposit found in Japan in the winter of 1700, which didn't have an earthquake to go with it. And there was historical evidence that this tsunami had arrived without an earthquake, which is very unusual. And so to shorten the story down, that's how we know that the last Cascadia Great Earthquake was January 26, 1700 at about 9 p.m. after back calculating the model time or the travel time from the arrival time in Japan. So Cascadia sort of went from zero to hero in a pretty short amount of time, and so this story is really a little delving into a little bit of how that came about. So an unlikely hypothesis, to be sure, and I mentioned that the original people working offshore were these folks down in the left. This list of folks down in the left corner, and one of the ships of the day was the Aquina, this Oregon State ship. Fairly small boat, but it could take deep sea cores. It didn't have any of the modern tools that we have today, but they did quite well with it. And so out of their work, so the people that worked, the people in this list were all hardcore sedimentologists. They did the grain size distributions, they did the heavy mineralogy, they did all the details of deep sea sediments and how they were transported off the continental margin into deep water. But they didn't, at the time, plate tectonics is only a few years old. This took place in the mid to late 1960s, and they didn't really think too much about the turbidity currents and what triggered them. They were just interested in their pathways, which are shown over here on the right, and the sediment distribution and the details. And so they laid down sort of a ground level framework of what was out there at the time. And it really, they didn't really seem to speculate much about what triggered these deep flows. It took John Adams to almost 20 years later to see something that the early workers couldn't see. And what he found was that in all these cores offshore, there was an ash layer. And that ash came from Mount Mazama, which is now known as Crater Lake, a big national park down in this corner. And when that mountain blew, much like St. Helens did, only much larger, it blew ash all over the Pacific Northwest. And that ash traveled down the rivers and wound up offshore in these channel systems. And what Adams noticed was that if you counted down from the top, there were 13 turbidity currents that occurred just after or after the laydown of the Mazama ash. And so that coincidence, though, is pretty odd. You see 13 here and 13 here, and it wasn't always exactly 13. There's 14 in some of the channels, but 13, 13, 13, so on. And it struck him that this is very odd because turbidity currents can be triggered by earthquakes, but they can also be triggered by other things, volcanic eruptions, storms, tsunamis, other things could mobilize sediments so that they would tumble down the continental margin and be accessible. But to have the same number in all these different sites struck him as very weird. What groupings of random events could wind up with the same count of events over 7,000 years, 7,600 years? And so he reasoned, well, the simplest way to explain this are the earthquakes that ruptured the entire margin the same number of times after Mount Mazama, 13 times. But what pulled it together really was looking at a confluence of several of these channels. There's one here and one here. And it has the same number of events on both sides of the confluence, and then the same number of events downstream of the confluence, still 13. And so really there were really only two possibilities. Either these were random events, and you would expect maybe 26 right at the confluence, and somehow downstream by attrition they lost a few, or lost 13 and wound up with 26, or these events wound up at the confluence at the same moment in time and traveled down, and you had 13 on both arms and downstream. And so the latter was sort of the outrageous hypothesis that these were synchronously triggered and without dating anything, without radiocarbon dating anything. He reasoned that these things were synchronous to within a few minutes. It's quite an outrageous hypothesis, and this paper was in 1991. And if you'll excuse me for just 1 second, my cat needs something. I'll be right back. Okay, sorry about that. So, so anyway, in this kind of crazy hypothesis, here's a better image of that. And a couple of us, Hans Nelson, who was one of the original OSU investigators, and I sort of became convinced that this was too much of a coincidence, too simple to be really a credible hypothesis. So we wrote a proposal to go out and disprove John Adams in the late 90s, because we just didn't buy it. And one of the things was that Hans Nelson was Mr. Astoria fan. So he'd done his PhD thesis on the Astoria submarine fan, and he just didn't buy Adams' arguments at all. He said, no, that's just not the case at all. There were really only three Holocene turbidites out there, not 13, as Adams had said. So we wrote an NSF proposal to go out and disprove John Adams, or test his hypothesis. And it turned out, though, that even in the middle of the cruise, while we were still at sea, we realized that John Adams was actually right and that we were wrong. And our cores are shown in, the original cores are in white, and our cores are shown in gray and other colors down here. And it turned out that although the details were slightly different, Adams was substantially correct. And so he gets really full credit for this hypothesis, which was done very elegantly on the desktop without ever going to sea, without radiocarbon dating anything, and just taking the basic observation of the distribution of the ash and this amazing coincidence. And so, in fact, in all likelihood, the last 13 Cascadia Great earthquakes were synchronous over most of the margin and delivered ash to this confluence right here within minutes of each other, coming from the north and from the south as well. And the interesting story is, this is the Melville, this is the ship we were on, and we were in the middle of this cruise on the Melville testing this hypothesis. And it's on the US ship sort of traditional to have a sort of dog and pony show for the ship's crew about what the cruise is about. And in the middle of this cruise, we had just realized that Adams was probably right. And so our dog and pony show shifted from how unlikely it was for all this to work to actually it did work as we were planning this talk for the ship's crew. And the ship's chief engineer came up to me afterwards, and he goes, I've been on this ship for 20-something years, and you scientists just are talking over my head all the time. I have no idea what you're talking about, but I can count to 13. I really understand what you're doing here for the first time. And we felt pretty, after having eaten a bunch of crow, so to speak, over our bad hypothesis, we felt pretty good about that. So then we were suddenly reluctant paleoseismologists. It works. So we completely failed, but became paleoseismologists and have been doing this sort of ever since. A big part of this story was you saw Adams' very simple diagram, and now we're able to go out and build detailed bathymetric maps of the region to help test the hypothesis and bolster the story. And so a big part of this has been building this image that you see here. That's taken over 20 years to collect this data. And originally, a lot of it was classified because the U.S. submarines operate in these canyons in sort of Red October fashion. And most of the bathymetry from these areas was classified up until actually 2008. But if we, anyway, meanwhile, back to the hypothesis. So synchronous triggering of these things sounds simple enough, and here's what that might look like if you had a great earthquake spanning the whole margin. So this is about 24 hours travel time, roughly, and showing the canyon systems as they actually are and the pathways that are defined by the modern bathymetry, but also by the core samples that were taken in the 60s and in multiple cruises since that time. And so we began to learn how to be paleoseismologists, how to sample, how to choose good sample sites so that they would represent the earthquake record and not other noisy signals like just random failures in steep canyon areas and things like that. And submarine canyon systems are much like subaerial river systems, and they have point bars and all the same sorts of features. And we began to learn how to sample these things so we'd get the record we wanted and not to sort of improve the signal to noise ratio. And then, of course, the tools we have today to look at core samples are much better than what they had in the 1960s. In the 60s, they basically had a hand lens and pencils and paper. And the most sophisticated thing would be a sort of low resolution, old style X-ray. But now we have something called multi-sensor core loggers, and this is a core going through one that's recovering magnetic data, density data, resistivity data, and all sorts of a whole series of wiggles representing the geophysics of the core sample. And so why is that important? At first, I really, being sort of a field geologist, but also a geophysicist, I didn't really realize the value of these little wiggles. But here's what a typical set of data would look like. So here's a core, here's a CT scan of a core and a hand diagram of what's in there. And these wiggles are shown here. So there's magnetic susceptibility in blue, grain size in the purple, density in the light blue, and P-wave velocity in the red. And so this is another example on the right. But what these things are really showing are proxies for grain size. So it turns out that the magnetics and the density and sometimes velocity and other properties are acting as proxies for grain size, which is good. So here's grain size on the right. You can see it has the same peaks as the magnetic susceptibility and the density, 3 in this case. And so this turns out to be important because grain size is a very labor-intensive, slow measurement to make. And when you have hundreds of meters of core, it would take the rest of your natural life to get grain size measurements over the full length of all those cores for, at half-centimeter intervals, which is about what we needed. So we needed a proxy to represent what was actually in these deposits. And the geophysical wiggles here fit that bill quite well. And then about 2008 or so, it became possible to start CT scanning the cores. And we have a good CT scanner at OSU, and these are becoming more common. This is becoming sort of the de facto standard for looking at these kinds of deposits. And so here's a CT image on the left, and then the other 3 images are separating out the sand fraction in blue from the silt fraction in green, and then the clay fraction in sort of reds and purples here. And so we can look into these deposits and inside the cores and see just more detail than you can imagine. Here's a worm burrow shown. Here the worm had lined its burrow with a little bit of silt, and you can actually see that. So armed with this sort of detail, then we started using a methodology developed in the oil industry starting in the 1920s to try to correlate these events. So John Adams had essentially correlated them in a very elegant way using relative dating. A thing had to happen at the same time as another thing, even if we don't know the exact timing all that well. And so he'd done that, but to test that, we radiocarbon dated all the events, and here are the radiocarbon ages. Here, they're probably hard to read, but in any case, we found consistent radiocarbon ages from site to site. And here's an example of 2 cores, 250 kilometers apart, with essentially the same sequence of events, with radiocarbon ages that fully overlap. But what the oil industry does is that approaches this in a different way. They want to track stratigraphy from one place to another. So if they have an oil-bearing deposited in one place that's making them a lot of money, they can then track it to another place, drill another hole, and make even more money. And so they use something called well log correlation, which is basically visual interpretation of these wiggles here to see if they match from one site to another. And so I think you can probably see here that these sequences are quite similar. The strong link here is this event called T11, which is the largest event on the margin, and it's ubiquitous in all the marine cores and also in lacustrine cores. Its age is about 6,000 years, plus or minus a bit. And so with that one kind of tying the record together, you can visually look, kind of inspect these sequences and see that they're quite similar. And to really do it, you need to spend several hours with these, looking at different possibilities to see, what's the probability that these sequences are the same or that they're different. And this is an interesting kind of thing. Signal correlation doesn't really work. It's geology. It's not really a signal per se. So automated methods really don't work on these things very well. And the oil industry, with unlimited resources, uses visual correlation just as we do, because the automated methods don't have much value. But to show you just one example of the strength of this, here are these 4 wiggles. These are 4 examples of that event T11 from different cores. Whoops, the wrong way. And here they are in context. So these represent 800 kilometers of span from the left side to the right side. And yet these cores look like they were collected right next to each other. They're so similar that the correlation is sort of unmistakable. And so we as reluctant paleoseismologists, started to build sort of a 3-legged stool where we had radiocarbon as one leg, the wiggle match correlations as another leg, and then the things like the confluence test of timing as maybe a 3rd leg. And the story in detail, as we dug into it, we realized how strong it really was. It was a remarkable thing that Adams did back in the 80s. And so here's sort of a finished diagram, simplifying this a bit, coloring in the wiggles so you can see the shape of the whole thing a little bit. And so these are 3 panels of 2 cores each, with hundreds of kilometers distance between the pairs. And in most cases, for example, Hydrate Ridge and Rogue Channel, these are two cores that are not only 250 kilometers apart, but they have no possibility of any interaction at all. This is in an upper or a mid-slope basin, and this one is in a channel system on the abyssal plain. So there's no possibility these things can interact, or their sediment distribution systems can interact in any way. And yet they look like they were taken right next to each other. And the same is true of the other panels here. So let me show you just visually a little bit more of that. So these bars are taken as just sediment thickness, just the event bed thickness, the simplest parameter that you could extract from these cores. And bed thickness is not a parameter that you would expect to correlate if the sequences were randomly derived from multiple sources. And so let's just, as an experiment, almost a thought experiment, just take the bed thicknesses from 4 cores that span the Cascadia margin from about the middle 800 kilometers worth. It's 1,000 kilometers long, so this is most of it. And just plot them here. And the only thing that's been done here is just to make the top and the bottom. We have a good marker horizon at the base of the whole scene, so we're confident of that independently. And so if we just stretch them out over the page, this is what they would look like. And if we do one simple thing to it and just do what's called flattening, that is, match the event bases of each one across the page, this is what it would look like. And suddenly sort of a chaotic jumble begins to look like matching barcodes a little bit. And then if we flatten and match the event tops in the same way, then they look pretty good. And so this is kind of a simple visual example of how good the correlations across Cascadia are. If we hang that on a time scale instead of just a visual scale, it just looks like this. And so there's some key bits that tie the story together. One is big gaps here between the 5th and 6th event tie the records together well at about 1500 to 2000 years. Another 1,000-year gap between the 10th and the 11th events is readily identifiable. And then here's T11, our sort of another key correlative event here. And T16, which I didn't mention, is another very large event down near the base of the Holocene. So, so throwing the book at Adams' original hypothesis just made it stronger, essentially. Here's just an example of a relatively new core added to the well-developed series that was published in 2012. And we'll just, the new core that was added is this one in the middle. So we took a core that was sort of a second stringer. It didn't have the full sequence at full throat as other cores. Its location wasn't ideal. But we came back and just tried to lay it in here and see if it would fit. And it actually worked out pretty well. It's this one here in the middle. And so we'll do the same trick where we're showing bed thickness of each turbidite bed as a black bar. And then we'll take away the data so you can just see the simple version of it. And then scrunch them together so you can have another look. And it's just kind of remarkable how well this works with a very simple parameter, which should not correlate. It's not perfect, though. You can see that this bed here is not present there. This bed here is not present there. And so there's some small differences for the smaller events. The big events are present in all cores, but the small events are more variable. And so once again, testing this confluence test of atoms, here it is in close-up detail, looking at it with more modern data. So here's the southern Willapa channel, let's call it, and the northern side is Fault2SHA channel. Here's the now famous confluence. Some of the original cores that Adams used are shown in white. The cores that we have available today to look at this are all these other small dots. So we have many more cores plus modern bathymetry data to look at. And it turns out that really to pass the confluence test down here, there are actually 7 other confluences that have to be satisfied for this test to actually work. And there's one more that's off the screen to the left, just barely. And so to wind up with the same number of events all the way down the courses of both sides of this, you need to pass 7 confluence tests in total for that to work. And so looking at some of these things in more detail, we can see systems like the Fault2SHA channel system wending its way through this active continental margin, and we can see the interactions between modern sedimentation and the growing accretionary wedge. So for example, this is a side scan image of that. Here's the leading edge of the continental margin right here, the first thrust, and here it is on the right, growing across this channel, and it's ponding mud, which is this dark stuff here. So fine-grained sediment is ponding behind this growing ridge. And so we can see many of the details of how the sediment distribution is being influenced by the growing active accretionary wedge, and use those to our advantage to help pick good core sites. So cores taken at sites like this typically are barren of Holocene turbidites because it's sort of a venturi. Things are moving too fast and there's non-deposition here. But cores in sites like this are beautiful. They're large, with a thick expanded section of this ponded material. And then we can also test things like alternative pathways. In a paper a couple of years ago, Brian Atwater proposed that there was a way to get turbidity currents over the top of the accretionary wedge and essentially short circuit the elegant confluence test of atoms. But it turned out that hydrodynamic modeling, which, let's see, shown here, showed that that really isn't possible, and I'll just zoom ahead and show the model. And so the shortcut is right over the top here, and it's really not very likely based on the hydrodynamic models. And so Adam's hypothesis, here's the more modern take on it. The number on the right here is the number of post-Mazama turbidites. So you can see 13, 13, 16. It's a little noisier than the original paper. 16, 12, so on. And then the number on the left is the total number for the Holocene, extending the record back from 7,600 years to 10,000, and it's around 19 or 20 in most cases. So this is sort of our final take on just the simple count as far as a test of the confluence. And then we compiled heavy mineral data for these things to see if there is a difference between one side and the other, and if that could be used. And sure enough, there is. This side, the southern side, is dominated by the provenance of Columbia River basalts, which are sourced to the south and east here, and the provenance coming from the Fraser River Delta in Canada dominates the heavy mineralogy coming down this side. And an important bit here is glaucophane, this little blue crystal here, present on the north side, not present coming from the south side, and so all of the cores on this side are observed to be absent of glaucophane. All of the cores on this side contain it, and then when you get down to the confluence, you can find turbidites downstream, which show a mixture of that as these materials mix and stack in to the flowing turbidity currents downstream. So that was kind of there's the glaucophane, there's the non-glaucophane. And there's where it isn't, and there's where it is. And so this was kind of the final test, really, of the details of Adam's desktop hypothesis. And again, it passed with flying colors. So it's always nice when an independent group comes along and tests your hypothesis and comes up with the same result. And this happened in 2015 when Tark Hamilton and a group of Canadian colleagues working at a place called the Slipstream Slide, which is imaged down here in the lower left, made a special little swale that they could core and then look at the turbidite sequence in this swale. And it's completely isolated from transport from other places. So this is a very locally derived record. And on the right, they correlated their Slipstream Slide data to our data on the right. And it's not perfect, but it's substantially the same record. So they were able to extend the turbidite record up into the northern limit of Cascadia. And so Cascadia has gone from just a complete question mark in, say, 1984 or so to now, I would argue, one of the best known major fault systems in the world, despite the fact that we haven't had a major historical earthquake on this system, instrumental or historic. And so, so what can we do with all that data? I mentioned Brian Atwater, but there have been scores of other people working in this, working on the land data in terms of tsunami deposits and subsided marshes and so forth. And so here's all the land data listed here in this brown box and all the marine data in the blue box. And this horrendously ugly diagram, you couldn't possibly interpret this in a few seconds, but I'll just walk you through it. The green bars are the best fitting radiocarbon ages, which would be sort of a minimum earthquake model, the smallest number of earthquakes that could satisfy all the data. The green lines are the well-log correlated turbidites here. And so this model is sort of a maximum model, the smallest number of large earthquakes that could satisfy all the data. And you can see there are a number of earthquakes or a number of events here that pass a more limited set of tests, but seem to represent smaller earthquakes in the southern part of the margin. So this is south on the right and north on the left. And so we seem to have a diversity of earthquake sources for these events, in addition to the large ones. But there's a much more fun way to look at all of these data than this unintelligible diagram. Here's just a zoom in of part of what that looks like. And the more fun way to look at this is if you have the strike extent from paleoseismology and the timing from paleoseismology, then you could actually put this in map view. And we have 46 examples of this, so we can play these map views as frames. And so I call this Cascadia the movie. This is the entire Holocene sequence. And this is interpreted, of course, from the geology. But we're going to play this backwards from the start of the Holocene at about 200 years a second. And let's see if it'll play. There it goes. Okay, so the dots you're seeing are the sites at which these events are represented in this interpretation. And the width of these rupture patches is just a pure guess, really. It's based on geophysics, but very loosely. The main thing that we have good control over is the timing and the strike length. And to some extent, the size in a relative sense. So we're about halfway through the Holocene now, 4,800 years. And right about here is where the land record begins to kick in. The Holocene record is about 10,000 years offshore and about 3,500 years onshore. And now you're seeing more sites light up onshore in coastal sites and also in lakes. And here's the San Andreas going off down here as well. Now we're down to 1,500 years ago. $800 years. $500 years. And then the now famous 1700 earthquake, January 26, 1700. Which is represented by this Hokusai print of the tsunami, which isn't really the 1700 tsunami, but it looks good there. And also what this represents down here is the fact that Native Americans were here at the time. So there is actually a record of the last Cascadia Great Earthquake, but it's in the form of a legend. And the legend is about the two great gods of the coastal tribes of North America at the time, Thunderbird and Whale. And Thunderbird and Whale had a tremendous battle at a time a long time ago, and there was a lot of thundering and shaking of the ground and big waves that washed away villages, which when you read these legends sound a lot like a great earthquake and tsunami. And so many people have interpreted the Battle of Thunderbird and Whale legend as really the historical record of the last Cascadia Great Earthquake. And so here's what a summary of all that would look like. We have about 20 events that seem to run most, if not all, of the full length of Cascadia. We have 3 or 4 more that stop a little bit short of that. Quite a few more, 8 or 9 that run up to about the latitude of Portland and the Columbia River, which are here. Several more that stop in central Cascadia and central Oregon. Quite a few more located in the far south, and even more located even further south, and just a single one located up in the northern segment. So, of course, earthquakes, as Hiro Kunimori said, it's not, earthquakes don't kill people, buildings kill people. And so one of the main drivers for all this is seismic hazards and public safety. And of course, this is what we would like earthquakes to be like, ruining the Etch-a-Sketch gallery. But realizing that that's probably not the case, the thing that people always want to know is what are the probabilities? Since we can't predict earthquakes, at least not yet, what we have is looking into the past. And so that's why paleoseismology, even though I got into it accidentally, that's what became so compelling about it. Because it's really our only tool to forecast earthquakes. It's looking into the past and looking at the probabilities. So if we take all of our data and just plot it here as a plot of unreliability, which means the fault will fail at some point near the top of the diagram, and plot all our data on it, we're very fortunate now, I think, in Cascadia that we have enough data that we can use real data to look at a plot like this as opposed to a recurrence model of some sort. And if we plot time across the bottom in a log-log plot, and then go out 50 years from the last earthquake, and this plot's now a couple of years old, and so that's our target date out here. And then look at where the data is relative to that. You can see that all these data points, which are the intervals between earthquakes, and their uncertainties lie to the right of our target date for the northern Cascadia margin. So this is mostly Washington. And so this just means that we have an average 430-year cycle, but we haven't reached even the median time for that. And most of the recurrence intervals for Washington are in the future, which is to the right on this plot. And we've only passed these ones on the left. So that leaves us with a probability of about 10 to 15% of one of these large earthquakes affecting the Washington margin in the next 50 years. On the other hand, if we make a similar plot and just divide Cascadia into a northern part and a southern part, just to simplify it a bit, and build the same sort of plot, our target age is out here, 360 years from the last earthquake, and plot our 46 earthquakes, so we have many more smaller events, we can see that most of these intervals here are actually in the past. So, and only 6 of them lie in the future. So what this is saying is that in the southern part of the margin, a geologically recordable earthquake occurs about every 240 years or so, and we're more than 320 years now into that cycle. So we've blown past most of these intervals, and we only have about 6 that are longer than that, than the 360 years since the last earthquake. So the probability is much higher of having some event. Now these are not all M9 earthquakes. These could be as low as 7s in some cases, but the probabilities are more like almost approaching 40% for some kind of geologically recordable earthquake in the next 50 years. And with such a data-rich environment, we can start looking at things like clustering of earthquakes. How evenly are these spread out in time? Is there some pattern to it? It turns out they are pretty well clustered, at least for part of it. So the last 5 events shown here are separated by a 1,000-year gap. And this is looking at the 20 large ones and sort of ignoring the small ones for the moment. A 1,000-year gap, and then another cluster of 5, and then another 1,000-year gap. And then the clustering is much less apparent if it's present at all in the early Holocene. And this is just another realization of that same data. So we use these 1,000-year gaps to help tie the record together. They're part of our correlation tool. But the meaning of it is highly debatable. Is this pattern meaningful in some way? If the 0 time here is you are here, can we use this to predict anything? And the answer at this point is no, not even close, because we don't really know if this clustering that's visually apparent has any, and it has statistical meaning, but does it have any physical meaning? Is it really just random, or is there something intrinsic behind it? So when we bring this down to people, what do we do with this information? I mean, we've all seen the 2011 earthquake in Tohoku, and it's odd to say this, but this is what success looks like in a great earthquake. Japan lost 20,000 people. The number isn't really even known very well. But at the same time, but Japan was one of the best prepared countries in the world. Sumatra, on the other hand, lost an order of magnitude more in a completely unprepared country. So if this is what success looks like, where do we stand in a place like Cascadia? We're not Japan, but we're not Sumatra either. And so in the Pacific Northwest, we have hundreds, thousands really, of unreinforced masonry buildings like these, where small magnitude earthquakes can essentially destroy the building. We haven't even begun to think about retrofitting buildings like this. just only in a few cases. We have hundreds of bridges like this that were built before plate tectonics. And most, if not all of these will come down, some of them, like the one on the right, barely look like they'd stand up to a strong breeze, let alone even a modest earthquake. And we have thousands of unreinforced masonry schools. And this one was the lucky beneficiary of a modest retrofit a few years ago, but there are many, many thousands more to go. So I visited Japan. I was actually in Japan for the last earthquake, just coincidentally at an earthquake meeting, and then went back to visit a few years later, and saw this. This is the Minami Sanriku Public Safety Building. This is Mayor Sato of this town of Minami Sanriku, and this building was occupied by people broadcasting radio warnings about the tsunami coming, and 48 people were killed at their stations in this building. And Mayor Sato was one of 6 to climb the cell tower on top of the building and watch his entire town go underwater during the tsunami. So flipping back to the Pacific Northwest, where do we stand? There are a few places that really stand out. This is a school in Seaside, Oregon, that was just recently rebuilt on high ground out of the tsunami zone that used to be down here in the lowlands. And so a few places in the Northwest are starting to get the idea that this is going to happen someday, and look forward to that future, and try to make the Pacific Northwest more resilient than it is now. On the other hand, my own university built a new building, it's not in this picture, but right here on a sandbar right in the tsunami zone, sort of inexplicably ignoring all the science. And I just can't help thinking, what would Mayor Sato do if he were the guy in charge of giving the building permit for this? And so I'm going to try to wrap it up there and see if you guys have any questions, things you'd like to talk about. Thank you.
Chris, thank you so much. Does anyone have any quick questions? Please either just raise your hand and you can say them aloud, or if not, do put them in the chat. And we have time for just 1 or 2 quick ones. Would you like to kick off? Yeah, Dylan, would you like to go ahead?
Hi, Chris. Thank you so much. That was so informative, and it was just a joy to listen to. I learned so much from it. Thank you so much. As a person who's just kind of moving north from California up into the Pacific Northwest, this was a perfect introduction. Thank you so much. I'm,
thank you.
Of course, thinking about going from south to north, and you kind of alluded to it in your abstract. There's this, lighting up of the northern San Andreas associated with a lot of those lighting up of the subduction zone. I'd love to hear what you're feeling on that problem, and the potential for some interaction between 2 different tectonic parts of the plate boundary.
Yeah. Thanks, Dylan. That's a great question. I'm actually working on that and was hoping to have enough time to talk about it. But it turns out that the San Andreas, we have a paleoseismic record that's a few years behind the Cascadia record in terms of the richness of land and marine data. Lots of people working on it, but so far what we have is, for about the last 4,000 years, about 3/4 of the San Andreas events are indistinguishable in time from Cascadia, and that's kind of a startling thing. We published a paper on it a few years ago, but again, with radiocarbon, with 200-year uncertainties, you could say, well, that's an interesting coincidence. But it seemed to be more than a coincidence to me. And so we went back and collected more cores and done more work on it. And it seems like it's much more than a coincidence. We think we're seeing stratigraphic evidence of both faults going off in close proximity in time, with turbidite stacked on top of each other. And the lower one, or the upper one, goes can be traced all the way to San Francisco, and the lower one fades out pretty quickly. So it looks like Cascadia is going off and influencing the San Andreas to go off at some later time. That's hard to determine. It could be minutes, it could be decades. There's really currently no way to tell. But even decades is pretty close if you're thinking about it in terms of public safety, to have two big disasters that close in time. Even if it's not minutes, even if it's years, it's pretty notable coincidence. And so it looks like it. So that story is kind of trundling along towards a paper, is not terribly quickly, but it looks like it's going to pan out as a viable hypothesis that the two faults are actually partially synchronized for the past few thousand years. And when you go to earlier times, they seem to go out of sync, and they're no longer synced up. So I got into reading papers by Chris Schultz and Joan Gomberg, and about fault synchronization and things like that, and I began to appreciate them a lot more after thinking about not just one triggering event, but what about a whole series over time. And there's actually a lot of reason to expect that faults with similar recurrence rates might sync up, not just randomly, but in a stress-strain relationship. But thanks for that. Sorry I didn't have time to show all the slides that go with that.
No, thank you so much.
Great. Well, thank you for the question. And Chris, thank you again. I think we all learned a lot about using the onshore and offshore paleoseismology, and about your story and about Cascadia as well. So I think that's given us a lot to think about, and your last comments as well. So thank you very much. And for everyone, we look forward to seeing you again on December the 12th, where we're going to learn about fragile geological features from Mark Sterling. So we look forward to that talk. It's slightly earlier in the day, to help with everybody's different time zones. I know we shift the time to try and help people not have to get up too early or stay up too late when they're across the world. So Chris, thank you again, and